15 seconds.
Is it recorded?
Yeah, they told me, yes. But not you, just me.
No, because usually in other courses it wasn't recorded.
Ah, yes, they asked, I don't care. I mean, if they want. So if they see some seeds flying to the blackboard, they won't get you. There is some machine delay, they told me, not something that after they press the button, still since the light has a kind of speed, they need 5 seconds. The recorder is in the space. Okay, so let's start. So really, the program is given, but the aim of the course is really the construction of the Lebesgue measure. Okay, so the Lebesgue measure is what? let me say something really precise. I'm sorry for people that already know. How many of you know the Lebesgue measure? I'm sorry, so many. In 1 dimension, 2 dimension, 3 dimension, several dimensions, any space. I'm sorry, but how many of you doesn't know the Lebesgue measure? Everybody knows the Lebesgue measure. Okay, this, are you sure? Everybody knows the Lebesgue measure. Okay, so then I'm sorry, last year nobody knew the Lebesgue measure. So, so I will do a little bit further. So the Lebesgue measure is, so let me ask you, what is the Lebesgue measure? People that know. So it is a measure, so you know what is a measure. So a measure is defined on what? On a sigma algebra of sets, and why this is the Lebesgue measure? So what is the characterization of the Lebesgue measure here?
Defining the Borel sets?
Mm.
What is defining the Borel sets?
What is the Borel measure?
Okay.
Okay, finally I found something that you don't know. So there is a characterization. So it's defined of some set, but then we construct which sets are Borel measurable, because when you define the measure, essentially you already can understand which are the sets. So, but the main properties is, what are the properties of the Lebesgue measure that you want to prescribe? So why is it so special? You know, you can start with several other measures, and we will see.
Translation invariant?
Yeah, translation invariant. Yeah, because we believe that the space, well, at least for the Euclidean space, no, is invariant. If I measure something here and then I move there, I measure the same point.
Additive.
Hmm?
Additive. It's additive.
It's a
Additive.
Subadditive.
subadditive.
No?
Subadditive.
Subadditive. Subadditive. Well, that's an outer measure. It's an outer measure.
Sigma subadditive.
Is an outer measure. But actually, I'm not asking you really technical. Is what you want to? Well, I want to measure something, and actually, I have a tool to measure. And so translation invariant is the fact that I measure something here, then I go there, and my tool is not going to change. But there is something else. Now, for example, if I have something which is 1 meter of length, my measure should give 1 meter. So the length,
The interval? The length of unit interval
Yes.
is 1.
or the length of an interval, so let's say it extends the length of intervals. Okay? And okay, now for integrals. And then finally, more or less the subadditivity was suggested, but I want really to have some. So if I cut my, let's say, if I cut my segment into pieces, the length is not going to change, no? So, and this is the first important observation. So it is sigma additive. So if let's say, let's call this measure M. So let's say M of the union of some sets. Let's say that I can give this the measure of the union if A n are disjoint is equal to the sum of the measure over n. Okay. So just one suggestion. Maybe when you apply to some position, they will ask you which that give me an example of measure. So this is the example of the measure, not citing all the strange measures like Dirac deltas. Yes, you have, but actually this is the important measure. Okay, very well. The problem is that so these three conditions cannot be fulfilled, and maybe you know, no? You know that you cannot. I mean, if you assume the axiom of choice,
Yes. It
otherwise,
can be extended by all subsets of, for example, R.
it cannot be extended to the whole set if you have the axiom of choice.
Yes.
Otherwise, well, the question cannot be. You cannot build sets, so it cannot be decided. Okay, so the aim now. So the aim of the first part. Okay, find sets such that the above condition holds. Okay, so in some sense, measure theory has these two. But once you know a measure, essentially you know the domain. The domain are the sets where, well, for the back measure you need to require this one, for the other measure you have this plus something else maybe, but actually it cannot be on the whole set in general. So this is. So let's see now a little bit what about the domain. But I'm sorry, because I prepared something, but let's go a little bit faster. So this means that the domain has the property that if A and are disjoint, well, for every union of set, you can make a union of disjoint sets. So essentially, you want to require that if AN belongs to the domain of N, also the union belongs. So together with the measure, you have what is called the sigma algebra. So, and the condition holds, and that is the definition of sigma algebra, which are pretty natural at the end. So a sigma algebra is a family, let's say, omega contained in the power set of well, here we live in R, or of any set, such that. Okay, let's see. Since you know, you have three conditions here, basically. So we'll start with the first. At least one set should be in, and which is the easiest one. The empty set. Now let's put the second one. Okay, by the rules in the set operation, you can switch a little bit which condition you want to put. No, because at the end you can say counter intersection, complementation, countable union, just put whatever you like, but let's do the standard way it is present.
Closed under countable union.
Countable union. And finally,
Differences.
the complementation. Simply because if you measure, if you have a set, and you know that a subset is a sum measure, you expect that the complement is the measure of the whole set minus the piece. So if A belongs to omega, here we are in R, otherwise in any set is in omega. Okay. So I prepare also some stupid exercises, and let's do first. So just to go on, how many of you knows, for example, some advanced the covering theorems?
So what?
Okay.
Covering theorems.
Covering theorems.
Yeah, Vitali, Vesikovic,
I know beta.
Vitali covering theorem. And the differentiation Radon-Nikodym theorem.
I know, but I don't remember very well.
Okay, so maybe we just go fast here just to settle the thing, and then we go to the. Actually, please answer. No, I don't know. Then I have to decide the speed. You understand? So which the pace of the lecture? Because if we are prepared, we can go to more advanced objects. Otherwise, we just stick with this basic thing. Now I prepare the basic. Well, I will run a little bit here, but we have to decide exactly which is better suited for you. So let me see how many of you can solve this exercise. For example, so is a sigma algebra. The power set of any set over R is a sigma algebra. You can say, I have some doubts. Many of you don't have doubts, maybe somebody has doubts. In that case, okay, you do the exercise. Then define the following object. If E is contained in R, the function is a set function, which I call measure. E of E is equal to the cardinality of E. So this is the cardinality.
Even if E is infinite?
That means infinite. So it's a set function. So let's see. Mi is translation invariant. Doubts about it? Mi is countably additive. But actually, mi is even uncountably additive here. Doubts about it? Well, you prove it. Let mi prime of E. Okay, the notation should be the indicator function of E evaluated at x bar. Then mi prime is countably additive.
This is the indicator or what? Indicator?
Indicator. So this means that this 1, if x bar is in E, and 0 if x bar is not in E. Okay, usually this is called the Dirac test. Is the node of an x.
Characteristic. Is it also called characteristic equation?
Characteristic equation.
Characteristic function.
This is the characteristic function, but usually this depends on the notation. Sometimes the characteristic function is 0 inside the set plus infinity outside. The indicator function is 0 outside and 1 inside the set. Just notation. I decided that since you have a 1 here, I prefer to think this as what you call the characteristic function. But it just, the important thing is the symbol, the meaning. Okay, so these are two examples of measures. Say, so the definition of a measure on omega sigma algebra. Okay, so let's give the properties here. So here we need two properties essentially. Okay, so the mean is a measure if mean of the empty set is 0. And for us it's positive, so mean of E is greater or equal than 0 for E in the sigma algebra. And finally, the countability. If En is joint, then the measure of the union of En, that's why the sigma algebra left the whole, is equal to the sum measure of En. And since the objects are positive, I don't have any, this is absolutely convergent. So I need to define how to sum. Okay. So now, the first thing is that, well, these are very easy examples, but are not the one you have to repeat when I ask you about an example of a measure, because they are too easy. And, well, they are important, but not as important as the Lebesgue measure. So, now we start with the construction of the Lebesgue measure. I will erase. Now, how many of you knows the outer measures? So I have to put outer because we will see later that you cannot build a Lebesgue measure on the power set of R. And in general, you cannot build unless for basically these two examples, you cannot build measures on the power set. If you, well, really the problem is what is the power set? Because the power set is defined as the set of subset, but then if you don't assume the axiom of choice, the sets which you can actually build are not so many. The result is that we will not enter into the details of this, but actually be careful that many results on, well, the construction of something which is non-measurable requires the axiom of choice. If you only construct things, everything you get is measured. Because you always start with segments, and you can perform only counter-remaining operations, and they are controlled by this assumption. So how many of you know what is the meaning of outer here?
Very well. Not very well. I don't remember.
You don't remember. So you know?
Yes, it should be sigma subadditive.
Sigma subadditive. I relaxed the one thing requiring the subadditive. So let's say the definition and now is defined on the power set. Let's call it now M star. I want to, because at the end we have the end. The power set of R into 0 plus infinity is an outer measure if, but this one, we will see that it will be automatic in the definition within just this character. The mean of the union of En is less or equal than the sum of the measure of En star of En. Okay, one observation is about this condition here. I forgot to say. Sometimes you forget it. In that case, there is a trivial measure, another trivial measure. Everything is plus infinity. Even the measure of the empty set is plus infinity. So you see immediately that here, well, who cares? The thing is always plus infinity on both sides. So the equality is automatic, because there's only one value.
I don't remember this. We are measuring countable unions, or we can measure arbitrary unions?
For an outer set, an outer measure is defined on the power set.
Okay.
Now I give you the definition. So you have to exhibit which number you give to any set in order to satisfy this condition.
Excuse me, what do you mean here by the measure would be infinity?
So if I assume that the measure of any set is equal to plus infinity, even the empty set, then there is nothing to prove, to check.
Yes.
Whatever, it's like saying that everything is 0. You don't have any space. Okay, so let's give now the definition. So the important thing is, in general, an outer measure on the power set of any set is something which is countably subadditive. So here I need to preserve so this is an outer measure, so the Lebesgue outer measure is, so what is M star of any set A? Okay, so let's reach the thing. So I have a very complicated set. So this is very complicated. Constructed by the axiom of choice. And then you want to measure it, and you have your say your tool to your gauge that can.
You can approximate it from outside by opening the by.
Yeah, this is what you do. What you do. So I start by saying, okay, I approximate first the length of this one, then the length of this one, and then I say, okay, more or less this should be the length. If it is not, well, now I refine a little bit, and then I take something a little bit sharper here, sharper here, sharper here. So at the end, what I'm doing, I'm taking countably many open intervals. You can, for in this case, you can take close, open, doesn't matter. But here, let's say open usually. And I give a measure. But then since I'm not exactly, I measure the object, not because it's very complicated. So I say, well, now the next iteration, I sharpen my estimate a little bit. So what I'm doing here, I'm taking the that A is contained in the union of some open intervals IN, which is more or less what I read on my tool when I measure one part of A. I say, well, this is covered, but this is it. And then every time I do that, I give a measure. So it is the sum of the length of IN. And now I want to specify, so this is my one-step operation. The next step operation is that, well, I want to be able to refine my estimate as much as I can. So the infimum here, yes. Is that clear? Well, so the definition is quite simple, no? You have just to think how I would measure some complicated object. I can give a first estimate, and then I want to preserve the ability to refine the estimate as much as I can, which is actually what you do at some point. Clearly, since we are finite beings, we have to stop. But in mathematics, you can imagine to go on forever. Okay. So this is the definition of the Lebesgue outer measure. And now we have to prove which property this function has. Okay, so let's do let's keep the definition and do some stupid questions here. I write the question, wait 5 seconds, 10 seconds, and then anybody that has trouble just. So if E is contained in F, M star of E less or equal than M star of F. Okay, problems? Okay, so how to do this exercise? Because it's a standard. Any covering of F? Yes. So in E, you are making the infimum in a larger sense. M star, from this definition of the empty set, is equal to 0. Problems? No, just take interval each other. M star of a single point is equal to 0. Just take an interval. X minus epsilon, X plus epsilon. So the length is 2 epsilon. M star of E is countable, is 0. Now,
it is clear from sub-identity.
We haven't proven that.
but we have still proved that it is subadditive.
We can cover.
Well, yeah, it's a proposition, but actually here we can do it.
If it is discrete, we can just apply the same argument because we can, I mean, if there is no limit point in this set, so we can just take a small neighborhood around every point, and as we change, the infimum clearly comes to 0.
If it is discrete, means that it is finite or it goes to
No,
infinity?
discrete means that I can separate each
And,
one.
yeah, but how to do that?
Because if it is discrete,
Yeah.
it means by definition that around every point there exists an epsilon such that the interval. Yes.
Okay.
And so as epsilon goes to 0, the
But
infimum.
how many? Because, sorry. So these are the set,
Yes.
and they go on, no?
Yes, around every point, I take a small epsilon, yes, and I do this for every point, okay? But first of all, I choose an epsilon and decompose it to a sum of infinite number of epsilons, epsilon 1 plus epsilon 2, blah, blah, blah,
Okay,
blah.
just do the same with
Yes.
the interval with psi.
So I choose first an epsilon
Minus 2 to the minus I
Yes.
epsilon, psi plus 2 to the minus 2 to the I epsilon, 2 to the minus I epsilon. And then the covering, so the sum of the length of this interval is less or equal than epsilon. Actually, yeah, it is epsilon. Okay? Okay. So the first thing, now we...
Less than or equal to 2 epsilon.
Ah, yeah, you're right. Minus 2 epsilon, yes. Okay, so now we prove the first thing we are interested in is that the length of a segment is, the outer measure of a segment is the length of the segment.
In fact, if I start from 1, it would be only 1 epsilon. It depends on the convention whether we start from 0 or 1. Because we would have, the 2 comes from the summation of 1 over 2i.
Yes. Yeah.
And so if we start from 0, it is 2, but if we start from 1,
No, it was 2 because minus epsilon plus epsilon, the length is 2. So the m star of a segment, and now let me put everything. B minus A. Well, clearly, on one hand, it will be large, will be lower, no? Cannot be larger. Because just take the segment and okay, we approximate here from outside. So the point is to show that it cannot be smaller. So first we do for the compact set. Compact is just because, okay, I can cancel. I just need this definition here. Because it's something that...
I take A minus epsilon, B plus epsilon.
Yeah, this proves that m star of A, B less or equal than B minus A. Why? Just A. I just take the covering A, B contain the A minus epsilon, B plus epsilon. So this implies m star of A, B less or equal than B minus A plus 2 epsilon, forward epsilon.
So, do we require the intervals to be open intervals? We haven't mentioned that.
Here, yeah, open. It's written here. It's very bad written, but it's open. This doesn't matter. It's just for, well, for other measures clearly it matters. For the back does not matter. But once you choose which one, well, it changes a little bit the proofs. Because here we are using that compact set can be covered by finitely many open sets. But clearly you see from the definition that if I take the open or the close, I'm just adding countably many points, and we prove before that countably many point is 0. And this does not depend if you take open or not. Okay. So this is the first point. Now we have to prove the opposite. So let IK, K is the open covering. then by compactness,
So it is covered by finitely, and we use the properties of the lens.
by finitely. So before it was in R, and then we have K I, and then we say I equal to 1 to some, let's say, as a matter n. And now, okay, I changed a little bit because the proof would be long, but I think we can have a picture of this one. The long picture is just to prove that the union of these points will make an interval, so which is larger than this guy, and so the sum of their length is larger than the original length. So let's see now graphically this object. So here I have A and here I have B, and let me define the indicator function of the interval AB. On the other hand, I can construct another function which is G, which is the sum over K of the indicator function over I, sorry, of each of the interval Ki. This is another function. It can only have natural numbers, so it can be 1 somewhere. I should need another thing. So let me, this is the original one, and then the other one can be 2, even sometimes 3. So it's the sum of all these pieces. Now what we know that it's a covering. So it means that for all x in AB, there exists I such that x, the indicator function of I of K of the interval I Ki in x is greater or equal, is 1 actually, because it is a covering. Okay? So this means that I cancel this point because it's the easy one. Do this here. This means that g of x is greater or equal than the indicator function of AB. You agree with this one? Yeah, because it's the definition of covering is equivalent to say that for each x, it belongs to an interval, which means this is 1. Now, the sum of this is greater or equal than 1. Okay? Final point is, what is the sum over I of the length of I, Ki? It is the area below the graph of this set, of this function. Is that okay? I mean, whatever is the, here is very easy. These are just rectangles. No? This is the area of the set y between 0 and g of x. And by this condition, this is larger than the area between y and the indicator function of AB, which is exactly the length of AB. Yeah, sometimes for something which is so immediate, you can find other proofs. Not this is just, in my opinion, fast because you see immediately what you are doing here. So the other proof is that you prove that actually the union of this set will be a larger interval than A, which is more or less hidden here. Okay, so finally, and right here we conclude then M star of AB is equal to B minus A. First. Now let's do the other.
Excuse me, in this graph of the indicators, one of the indicators is greater than. Yes, I mean at maximum it should be 1, so it can't be that one of them is higher than the other, right?
Can be.
How it can be? It is
The G.
Ah, this is just G.
G.
Okay.
G, yes, because you can have
Yes.
two pieces.
Ah,
So we want to call that this interval, and then you have these two open intervals now. So G becomes 1, 2,
Yes.
1.
Yes.
Just so finite Riemanni here is used just in order not to require
Convergence.
some other definition. What is the area of something which is unbounded? Here, finite Riemanni is very easy. They are just a union of disjoint rectangles. So the area is the sum. Okay, so let's do M star of AB. Okay, so we know that is less or equal than B minus A because this is already a cover. How to do the opposite? Use monotonicity. Here, by monotonicity is done. Because now you know.
But can't we say that the closed interval is just this union two points, and so if we take the outer measure,
It's always the minus, you don't know, because you're not saying, well, at the end it's 2, yes. But actually,
I'm trying to
Yeah,
get
it's
used
true.
to that the outer measure of a point is 0.
but you cannot, then you can never subtract.
Yes. That's
But more or less, yes, you can do the proof, but the problem is that you require a little bit additional computation. While here is immediate, because you know that this is larger or equal than M star, and now you take the closest set A plus epsilon, B minus epsilon closed. And this is B minus A minus 2 epsilon for all epsilon. Okay. So from this you get also the others, no? For bounded sets. For unbounded, again for monotonicity. So from this guy, well, for unbounded, so let's say the others, same proof. So because once you have an essay for this one, you just use that. You can use the closer to approximate the compact, to approximate anything. For unbounded, okay, same proof. So for example, unbounded A plus infinity is the union of A plus epsilon and now the measure of this guy is n minus A, so you have that the measure of A plus infinity is greater or equal than n minus A minus epsilon. Okay, that's it. It is plus infinity. Okay, question here? So, before going on, okay, let me finish the lecture and then we discuss it. So this is the first property, so it's really an extension of the length. And the second is the translation invariant. should I give a proof or you see immediately why? So let me just say by definition. M star of E is the infinite.
You can also translate the couples.
Code. Yeah, so if you translate, you get one inequality, then you translate back, you get the second inequality. Okay? So let's say, and coverings, let's say, and the sum of L I n plus y to the sum L, because the length is translation impact. So another easy proof, easy proposition. M star is countably suradditive. So M star of the union of En, whatever are the En, is less or equal than the sum M star of En. Proof how to do that. Just think, we have to think about the definition, no? So the less or equal means that here you're taking the minimum in a larger set. So it means that when you take something here, certainly belongs to the domain with respect to the infinite here. Okay, so if I n k is a open covering of En, which means that the union over k, I n k contains En, and the I and k are open intervals, then the union over nk of R and k is a countable open covering. Of the union of En. Do you agree? Yes. Okay, so that's the key point, but still there is a trick. How to prove that is hold?
Change of summations.
Okay, so let's do. You have first to say that if one of those is plus infinity, there is nothing to prove. No?
Yes.
Otherwise, they are finite. And then, so I can satisfy. So let's say this is the key point. And usually, it's really the most important part to understand the key point. And then now it's just technique. It's a standard thing. So I need to use actually a covering only. So the covering is an estimate only if it is not plus infinity, because otherwise it's plus infinity. And there is nothing to prove. So if M star of En is equal to plus infinity for some n, then nothing to prove. Otherwise, Otherwise, the approach is similar to how to the proof that a countable set has outer measure 0. For all n there exists E and K, the covering such that should be for all epsilon, for all n, such that the sum of the length of I and K over K is less or equal than m star of En plus epsilon 2 to the minus n. Because being the infimum and being not plus infinity, there is something which is otherwise always plus infinity. And then now you can, for the covering, here, so this guy, so I and K, now and K, we have that the measure of the length, okay, is less or equal than, okay, everything is positive, so it doesn't matter the way I'm summing them. So I can just decipher to fix K, N and sum all the K's. And when I sum all the K's, I can use this guy here. So it's M star of En plus the rest. Sum epsilon 2 to the minus n. Okay, so I have a covering which is less or essentially is less or equal than this guy plus epsilon. Okay? Is like for the countable length. So let's see some stupid exercises here. So the only fun is that you don't have much tools. So you have just to use the tools we have. So for example, the outer measure of 0, 1 minus the rational number is equal to 1. Less or equal than 1? Yes. But so you take a covering and then okay, this is fun. Right? So now let's do some remark. So if O is contained in R is open, then O is the union of open intervals, disjoint open intervals. Doubts about it? Just pick a point and take the largest connected set, the component. No? So M star of E is the infimum of the M star, well, let's say of the, I should say, here I should say what is let me be a little bit imprecise. M star of O, and O is open E contained in O. Actually, we did for segments, but finally, you see that if I have an opening, I have to prove that M star of an open set is equal to an open set, which was we prove for a single interval, and then well, we will see later that it's equal. You can either prove it or just accept. So in some sense, I'm taking the infimum over open sets containing the given set. This is exactly what I'm doing. If, let's say, G is the intersection of open set, then G is a G delta set. G delta set. This is a little bit of descriptive measure theory. And if F is the union of Cn closed, then F is called F sigma set. So in some sense are the easy sets you can build from the topology using only countable intersection and complementation, which is the two operations of the sigma. Actually, of the sigma algebra. So the exercise is proof that
Excuse me, here is the G itself, it's called
G delta set. If I say G is a D delta set, it's the countable intersection of open sets. Proof that M star of E is equal to M star of G. E is contained in G, and G is a G delta set. This is by definition. So essentially, actually you're not measuring any set, you're just measuring the smallest G delta set containing the set. So it's a regular sets. Not so nice, but actually at the end they are quite regular. And another exercise. So the fact that you assume countably many operations change a lot the situation. Now finally many are in trouble. Indeed, you can put the following. If ik from 1 to n is finite, open covering of Q, intersection 0, 1, then the sum of the length of ik is equal to 1. See why? No. Just that there is the trick is that the union well, there are probably other proofs. What I see is that the union of finitely many closed set is closed. And the closure of Q in 0, 1 is 0, 1. So essentially, since it's finite, I can more or less take the closure and see that immediately I cover the interval. And the closure is just
dense.
Hmm?
Because Q is dense, it's
Yeah.
dense.
And the closure is just adding finitely many points. You see, this is a
One of the intervals could be, it's a triviality, but one of the intervals could be outside of the interval 0 and 1.
Yeah, you're right. Sorry, greater. Yeah, this is the standard. Yes, I want just to prove that in that case, if you want to build the infimum with finitely many, you don't get the right measure. You don't have enough resolution. And another thing which is the following. If, let's say, the distance of A, B greater than 0, which means that what is the distance between two sets?
That means في مموت the distance between
Yeah, if x in A, y in B, or x minus y. Then m star of A well, we know the inequality, the other is just that you can really, from one covering here, build two smaller covering from the other.
It's the same as saying they don't have intersection?
Hmm?
Is it the same as saying they don't have intersection?
No,
because you can
no. The trick here is that since it is a positive distance,
Yes.
well, you have to open sets containing both.
for example 1 over n and minus 1 over n they are disjoint but the distance between the two sets is 0.
Yeah, but you're asking if this condition means that you're asking why it is false only when the distance. You're asking if this condition implies that they are disjoint, or if they are disjoint, you get this condition. No, okay. So here's what was the question. No, it's stronger.
Yes.
Okay. So now the next step is after this place to build the sigma algebra. So now we have something which gives you a number which extends the length to any set, whatever it is, I don't care. But say I want to preserve this property for countably many sets. And I forgot to say at the beginning, the main reason is that once you preserve this countable additivity, essentially it helps you to study the limit. Passing to the limit is trivial in many cases. And that's another strength of the measure theory. So actually you can really pass to the so countable union of sets, you just pass to the limit. And sum of function, you just pass to the limit because it's more or less like countable union, and then since the supon the sum is more or less like the limit, so now we have to build the sigma algebra, which is the domain of the level set. So this is the second part. So that is 1 hour and a half, no? So sometimes, in this course, we will only see basically the Lebesgue measure. So if I just say measurable set, it means the Lebesgue measurable set. Otherwise, well, I will try to specify with respect to this measure. So now I would like you to give the characterization of which set should be correct. So essentially, a condition on the set. So let's start. So this is just a data.
It divides correctly. The measure of the divisions is correctly summed.
Yeah, the measure of the division is correct. More or less this is the condition. So we start with something we would like the measure of A with the disjoint What is the trouble here is that this is a condition on two sets. I want a condition on one set.
So we can call always the union a new set C, and so.
But you know. Okay, so the trick is that I just let, for example, let me say this guy, so I fix, for example, there is a little bit of a jump. I believe they needed some time to find it. So let me just write what I would like to replace. Okay, I want to fix a set. So for example, I fix E. So here I make this free. So let's call it C, as it says. And I want to divide into two parts, and the two parts are divided by the set that is under consideration. So I say M star of C intersection E plus M star of C minus E. So now there is only, so E is the set that I'm testing, and I let C to be free. Okay, so it resembles this guy. The only thing is that now I have one condition on a set, or a set family of conditions on a given set. So I say that E is measurable if this holds for all C. The power set.
For all,
I think C, I think we reversed the order. Didn't we reverse the order like this? That C is now called measurable?
No. E is the measurable set that you are testing with all the C.
In this case, shouldn't this be E difference E? E difference C, because now C could be anything. So I'm measuring something outside E.
Yeah, but yes. In that case, it's trivial because this guy is 0 and this is C. But if you partition E according to any set C, you should have the equality. So it's a condition on E.
Yes.
Okay, so this is the definition. So the definition is a little bit strange, but actually, you see, it's just the idea is how to translate a condition that I want into something which depends only on one set. So I'm given this set and I'm saying, okay, let's cut in any way here. So let's use E to cut any other set, and then I should preserve the equality. Okay. Okay, so trivially, one equality is less or equal. So the less or equal, so let's say so the remark is that so the less or equal is my subadditive. So we have only true greater or equal for M star of C less than plus infinity, no? Because otherwise there is nothing to prove. Okay, so let's do the following stupid observation. Lemma M star of E equal to 0, then E is measurable. Questions here? Okay, let's do. So let me keep the equality. And, Okay, take MC. Well, first I would start just how to do this proof. I'll just take MC and see what happens. So I have M star of C on one hand, and on the I will write nothing here. I have M star of C intersection E plus M star of C minus E.
We can use monotonicity.
Monotonicity here. Yeah. So, what is the value of this guy?
0.
0, because it's contained in this guy. So, equal to 0 by monotonicity. And then, what I discover?
That this
Again by monotonicity. This guy is contained in this guy. So, here, by monotonicity. Okay. So, sets whose outer measure is 0 are certainly measured. And, well, we will see, I think, later that in this proof it tells you that you have sets which are not Borel, but they are measured. It's just a cardinality thing. Borel sets has the cardinality, there's some cardinality, and then you have of the continuum, and then the cardinality of subset of a set which has a cardinality like of the continuum as larger. So you have so many sets that cannot be all Borel. So here I don't need really the axiom or the choice. Okay, so let's go on. So the aim is to prove that the measurable sets are sigma algebra. So the second thing is that countable union of measurable sets is measured. Oh, sorry, let's start with finite, it's better. We divide it in finite, because there are also the text goes like this. Okay, so graphically, and then you build the series of equalities. Okay, so I have A, E1, and E2. Because I always like to approach the proof like you don't know how is the proof. You have to build is the game. So okay, so any idea here?
So A is the C is our C?
A is our C, yes. Okay, let's call it C as well. Yeah. Just because there in the notes I have some.
So can't we use just the distribution over union, intersection over union, and
Yeah, we need just to partition in a smart way, no? Using that E1 and E2. So essentially, we want to prove that the measure of this guy is the measure of this guy plus the measure of this guy, no? So I have to prove that the measure of this guy, plus the measure of what is left is the measure of the whole. now what I know for sure that the whole, well, I can take one piece, no? Is the measure of this guy plus the measure of this guy, because E1 is measurable. So this is E2. Okay?
But it also equals other
Yes.
equation.
So, but this guy can be used as a test for E2. So I have the measure of this guy, and now I got the first part, plus the measure of what is left, which is this piece here, plus this measure of what is left, which is the piece here. I'm using that this C minus E1 as a test for the measurability of E2. Is that okay for you? Well, I can write the series of equalities, no? But here I think you understand which is how to do the sum. And finally, I have to prove that the sum of these two is the measure of this guy. And what I use again. E1 is measurable. So E1 is measurable means that if I use this set as a test of E1, I have that its measure, its outer measure, is the sum of this piece plus that piece. Okay? And so this guy, so here I'm using that this guy is this guy, and here I'm using that this guy is that guy. So it's complicated. If you prefer, I can just write this sequence. I mean, it's just to replace each piece with the corresponding formula, and then you get the equation.
I have never ever thought that I will see the sign of Batman in a measure theory class.
That what? This, that?
Batman.
So now we reach finally the sigma dt. Now, pk is okay, this actually is a corollary, but it's finite and this joint measurable sets. Then for any A, the measure of the intersection with the union, so it's the additivity, well, in some sense, is the sum over K of the outer measure of the intersection, which equal. Okay. So more or less, it is something inside here, no? It's already written. And this is a corollary, because if you check, now, if you think it's just enough proving for 2, no? If you think here, this guy has disappeared, and this guy is exactly so there are these two guys, sorry, this part does not exist. So So the second part is exactly the intersection of A minus AK. So let's see with formulas now, just to change. So M star of A intersection the union just by I2. Because then you can iterate. Okay, now U1 is measurable, so I can say that it is M star of A intersection U1 union E2 intersection U1 plus M star A intersection U1 union E2 minus E1. And here I'm using that E1 measure. Now just observe that being disjoint, this guy is only A intersection E1. And this guy here being disjoint, just A intersection E2. So, okay, we conclude with this remark, and then we so is M is the family of Lebesgue measurable sets. Then, what we have proved here is that, well, the countable union is a set, and we didn't prove the, then I forgot to say first remark. But, okay, let's see then. So M is closed for complementation. And this we didn't prove, but actually M star of A equal to M star of A intersection E plus M star of A minus E is symmetric for E and the complement of E. Just because this will be the intersection with the complement, it is A minus the complement. Okay? And then we have that M is closed for countable union. And now we need the unit. The empty set belongs to M, because the empty set is M star equal to 0, no? So it means that it is an algebra. An algebra of set is exactly, well, it depends on the definition, because you can say that it's closed under countable intersection, but actually you have the complementation. Which takes care of that. So this is an algebra of set, and the sigma algebra of set is just when you replace the union, finite union. We have just proved this, finite union. This is the algebra of set. Sigma algebra is when it is closed by countable union. So now we have also this why the name is like that. So it is an algebra of set closed by countable union. Sigma algebra, if algebra of sets plus closure for countable union. Okay, I'll finish it today. Just one remark is that if you go on with the work, you observe that this countable closure is very close to the, well, it is my feeling, of course, it's close to the construction of the real numbers. That's why in some sense it works. It works very well. And so to end, let me ask you if I should go faster, slower, or it's okay like this. You can think and then let me know. Another thing is that if you, usually I prepare these lectures, they are in PDF, handwritten but PDF. So if you give me an email, I can send to you. You don't need to take notes, but just print out for the next lecture and then just take notes next to the paper. So, does anybody wants to give me the email? No, just I have the beach rolls if you want.
We write where we write.
I can write either one of you or for me it's not a problem to have more recipients. So just.
So if you have, if you give your email, so we all have in our group, and you can
Yeah,
say
yes,
you can
of
say
course. Yeah, also for any problem. Binchin without the final I, because I'm very old. When I started, the maximal length was 8. The name is Bianchini in Italian, so I should have a final I, but here there is no I because when I got the accounts was many years ago. I think it even works if you write Stefano Tisenave alias, but never use it. There are some others somewhere. I don't know. Okay, so if you write me, I can send the lectures. Okay, so Friday is the next one.
Do you think it's also
I'm not sure.